and why. And we have our speaker with us, Dr. Anishya Harshan from, yes, I'm sorry, going to be, and from MS12. Anishya Di graduated from ISA in 2017, majoring in physics. She is currently a PhD student at the University of New South Wales, Sydney, working the formation and evolution of galaxies. It is great to know that one of her PhD supervisors is Dr. Anshu Gupta, who talked in yesterday's session with us. In today's talk, Anishya Di will introduce us to the various pathways that the environment of galaxy affects its evolution, and will explain how the nature of the environment of the galaxy itself pushes the massive galaxy towards their end. It is a great pleasure to have her with us. With that, I hand it over to Anishya Di. Thank you.
Great. Thank you so much, Khushi, and everybody else. It's a great pleasure to be here and talk to you all today. I certainly brings back lots of great memories from ISA. I will quickly share my screen and hopefully it is visible. Okay, as Khushi introduced, my name is Anishya Harshan. I'm finally a PhD student at the University of New South Wales, and I'm working on the formation and evolution of galaxies in the early universe. I named the title of, so I'm going to be mainly talking about a recent project that I finished, and in this we look at which I've named as Beginning of the End for Massive Protoclastic Galaxies at redshift of 2 and why environment matters. So before I go into the more sciencey things, I was asked to talk a bit about my journey and so on. So let me quickly just introduce myself and what I've done so far. Even before I started at ISA, let's say. So I started ISA Mohali in 2012, and I was there till, of course, 2017. So that's my 5 greatest cherished years of my life so far. I think when I started ISA Mohali, I did not really know what to expect from ISA because I did not really have anybody else in my family or acquaintances who had a career in science. So I really had no expectations of what I will experience at ISA or what will come out of it at the end of it. But in ISA, I of course met most of my very close friends today, whom I'm still in contact with, of course, that's where I learned about astronomy and all the other sciences as well, and got inspired by so many different professors and all the science that was going on. I must say that as ISA, I was not probably the most exam-oriented student. I was very average, but what I did do at ISA, which kind of pushed me to this direction of hopefully getting a career in science, is the summer projects, most definitely. And I hope that all of you are also taking use of that. During my summer projects, I worked on different things from theoretical, numerical things in astronomy. And then I worked for some time at NCRA, where I worked with some of the observational data from radio telescope in Pune, which is the GMRT, for my last summer project. And that is really what pushed me to, or got me interested in galaxy evolution and most definitely, observational side of things. These are some of my friends, and on one of the 5 Onam celebrations that we had at ISA and some of our crazy time in Chandigarh, and you may see some of faces that you can probably recognize over here, which was the astronomy club or the astronomy group at ISA when I was about to graduate. And so after doing my bachelor's and master's in physics, of course, from ISA, I was applying for a lot of different positions. After many, many rejections, I got a position at UNSW, where I am right now. And my years in Sydney, which is where I'm right now, it has been very productive and very exciting. And I believe ICER has played most definitely a very pivotal role in shaping of even who I am today, and most definitely my research work as well. Of course, I've mentioned the summer projects, which has greatly influenced me, but I would also highlight the interdisciplinary work or the courses that we actually did at ICER, which sort of made me capable to talk to other PhD students and not just people who are doing astronomy. And that kind of pushes you to understand other subjects and find fascination in science, which is something that I cherish quite a lot. And that would not have been so if it was not for ICER Mohali, because I did have like 1 week experience in another university where I had just joined for like a week at the university. And the environment there was very different from what I had experienced in ICER. Even in the very first week, ICER was much more research oriented, whereas the Delhi University course was much more just learning the science that was there. And a lot of students had very different career plans, whereas most of my friends or peers in ICER Mohali kind of went into science. Not all of them, but a lot of them did, and they're all doing decently very well in their respective fields. So I do think the interdisciplinary work and the summer projects kind of built me up, and most definitely some of the other students as well that I know of, and hopefully in the coming years, as the alumni is getting older and older and getting higher and higher into their careers, going higher and higher in the careers, we can see the effects of that showing up. Most definitely, after ICER, when I thought my tryst with ICER was over, like a good dream, and I'm woken up and come to Sydney, it was not the case. Because soon after I joined UNSW, I learned that Anshu Gupta, who was one of the first, I think the second batch that graduated from ICER Mohali, was going to be my supervisor. And I think that is exactly what I meant. As we grow older, we'll hopefully be seeing lots of senior scientists and such like that from ICER Mohali, and it will be a great pleasure to know all of them in the future. And hopefully I can be part of that as well. So as you can see, this is me and Anshu at VLT, which is a very large telescope in Chile. And both of us smiling. She's my supervisor now, and it has been a great pleasure to have. It's almost like having a family member supervising me through my PhD, and it's been super great. So coming out of ICER or even before, like I went from not knowing anything about a career in astronomy or in science to hopefully have one soon enough. I've learned so much, and I hope that you guys are also enjoying the first part of it at ICER Mohali at least. So I've learned a lot, some of them really great things and some of them not so great things. For example, when I started my PhD journey here, and I learned that I will be studying galaxy clusters, this is what I thought I'll be studying. And, these beautiful, magnificent things I'll be looking at. And it was a rude awakening that I would actually be studying some things that kind of look like this. Because I'm studying high redshift universe, this kind of just looks like a random patch in sky, but there is actually a protocluster there. And you know what? These 5 dots of galaxies are it. In my first publication, my sample size was essentially just 7-8 galaxies, because that's just how many galaxies are there in the protoclusters that early on with decent data, which was a rude awakening. But since then, I've come a long way, I hope, and I've come to love the lots of different mysteries that high redshift universe still holds. And it is a very dynamic field in astronomy right now, especially with the JWST, which is the James Webb Space Telescope, going up, which will be telling us all about the very beautiful universe that we kind of live in and how it came to be in the very early universe. So this kind of brings me to the more sciencey part of the talk. I will now talk about the work that I was mentioning, which I have titled The Beginning of the End for Massive Protocluster Galaxies at Redshift of 2 and Why Environment Matter. So for the rest of the talk, I have kind of divided the talk into 3 parts. One will be the beginning of the end, one would be redshift of 2, and the other would be why environment matters. So I will start by why environment matters. So we know that the universe is about 13.8 billion years old since the Big Bang. And since the Big Bang, the first stars appeared, first galaxies appeared at around 400 million years, when the universe was just 400 million years, and it reionized the universe for another billion years or so. And after that, these galaxies sort of started clustering together and started to form protoclusters, which kind of grew and grew to become the clusters that we see today in the local universe. And as you can see in the local universe right about here, there is a very large variety of different morphologies, different colors, different star formation properties, metallicities, and so on in the galaxy population. So one of the studies is, one of the things that we are trying to answer is that how did this diverse population come about in our universe? And one of the things that actually affect this diversity or brings about this diversity is the environment of the galaxy, which is what I have been looking at for my PhD work. Environment of a galaxy can be defined in various different ways, really, but broadly classified into 3. Which is the isolated, group, or cluster environments. Isolated galaxies, or the field galaxies, are galaxies that are sort of not in near vicinity with other galaxies. They are not gravitationally bound to any other systems. They are kind of on their own and mostly evolving without any hindrances from outside. Other group environment is a group environment where the galaxies are together with a few other galaxies, like tens of galaxies, and they are all gravitationally bound together, so they may be interacting with each other as well. And the most highest density environment is the cluster environment, where thousands of galaxies are gravitationally bound. There's a massive dark matter halo, and they're all interacting with each other and the halo and the intercluster medium and so on to form this, and which kind of constitutes of the most densest regions in the cosmic web today. You can liken this different environments to our peoples as well. I always like to say in the beginning of these talks that galaxies are kind of like people. They can be isolated, because I'm in Australia, isolated like a kangaroo in the outback of Australia, or you can be like with a few friends in the, like a small town or so on, which could be a group of galaxies, or it could be like a cluster, which is like big cities like Delhi or Sydney, where there's too many people very close to each other, and you are most definitely bound to bump into somebody or the other. So galaxies that are in different environments, these go through different processes that kind of diverge their evolution from each other. And so how does that happen then? Galaxies that are more in very high density environments, because there are more galaxies nearby, they will go through interactions with other galaxies. Now, these interactions could be like mergers, when the galaxies kind of sort of go together and they merge with each other to form a new galaxies with completely different properties from the ones before, or depending on the mergers, the properties can change of the resultant galaxy as well. Sometimes galaxy just kind of flies by nearly from other galaxies, and that can, because of their gravitational pull, that can take away some of the gas and stars from the galaxy. That is called tidal interactions. Sometimes the galaxy, as they're falling into this big cluster potential, which also has a lot of intracluster medium, which is just the hot gas that kind of surrounds all of the space that is in between the galaxies. In the cluster, it's called the intercluster medium. So as the galaxy is falling through that intercluster medium, interacting with the potential of the cluster itself, the intercluster medium sort of acts as a viscous force against the galaxy. So the gas that is in the outskirts of the galaxy or is less bound to the galaxy can be stripped off, and that's called ramp pressure stripping. Now the intercluster medium is hot because there's lots of activity happening, and so galaxy may not be able to cool down effectively, and it can heat up the gas inside, and that will sort of diffuse the galaxy a bit. That's called thermal evaporation, and again, because it's in a higher density environment and it's hot, sorry, I'm getting a bit of feedback. Okay, thank you. Is it okay?
It seems I know.
Okay. Yeah. So as galaxy is in a hot environment, it is not able to get more gas from the outside, which can be used to make more stars. So it kind of starves itself, and that's called starvation or strangulation. So all of these different processes are happening or being experienced by these galaxies, sometimes at the same time. And these kind of processes can change the star formation in the galaxy, metallicity of the galaxy, morphology of the galaxies, and so on and so forth. And that really brings about the diversity in the population of galaxies that we see today. Now, the effect of environment on the galaxies was first observed, or most established result is in the galaxy density relation. As you can see here, this is a Hubble's view of galaxy cluster, which shows many different galaxy morphologies. As you can see, these galaxies over here, which are part of the cluster, they are much more yellow, they are elliptical, which means that they're probably not making as much stars, whereas the other galaxies around the same sizes, they kind of look more blue, they are more spiral, some of them have bars, so they are probably making a different amount of stars and so on. So there's very wide variety within the galaxy of galaxy properties within the galaxy cluster as well. So the first established result in the effect of environment on galaxies was the galaxy morphology density relation. What morphology density relation tells us is that the galaxies that are spiral usually are bluer and they are making much more stars. The fraction of these spiral galaxies decreases as we go into the higher density environment. So the x-axis here is just the density of the galaxies, or the number density of galaxies in the space. Whereas the galaxies that are lenticular or elliptical, which are usually not making as much stars, as you can see here, which are more redder and they do not have the beautiful spiral arms in them, they kind of just look like big fuzzy blobs. They are very massive as well usually. So the fraction of these galaxies that are not forming as much stars kind of go up. So this also shows us that the star formation of the galaxy is probably being affected as well, because the morphology is very closely correlated with the star formation of the galaxy as well. So besides the morphology density relation, then we also see this direct effect very directly in the star formation rates of the galaxies. Here, the x-axis is the distance of the galaxy from the center of the cluster, and the y-axis is the star formation rate of the galaxy. So you can see outside of the cluster center, a cluster which is in blue, shaded in blue, or where the galaxy is called field galaxies, they have a very flat star formation rate. So that means the star formation rate of the galaxy outside of the cluster is not dependent upon or correlated with the radius of the radial distance of the galaxy from the cluster center. Whereas the galaxies in the cluster, we have, as we go closer and closer to the cluster center, has a decreasing star formation rates. So that means that galaxies, that once they become part of the cluster, are being affected by the environment and their star formation rate decreases. So that is what I mean by the beginning of, or the end of the galaxy, end of the star formation rates of the star formation in the galaxy. And this process is also called the quenching of the galaxies. So this result is very visible at the local universe where the galaxy clusters are already well formed, they are virialized, they're very massive as well. But how did this effect start to form or start is not something that is very well understood. And that is why we are looking at redshift of 2. At redshift of 2, the clusters are just starting to form and they are called proto-clusters. They kind of look like this. It's not very dense as we saw earlier in the cluster, which was at redshift 0. You can see that there are some galaxies, because of course this is not HST imaging, and even because they're also very far away, even if we had HST imaging of this one here, we would not really be able to see the multiple different morphologies as we saw at redshift of 2. But what you can see is that the density is not as much. So the galaxy cluster is still just starting to form. So that is why they're also called the protocluster. But even at redshift of 2, in such protocluster, we see a slight effect of star environment on the star formation rates of the galaxy. So again, on the y-axis is the star formation rate of the galaxy, and on the x-axis is the stellar mass of the galaxy. And we can see that the blue line, which shows the field galaxy, is slightly higher in star formation rates compared to the red galaxies, which are the cluster galaxies. So that means even as early as redshift of 2, the galaxies in the cluster are starting to show a little bit less star formation rate. Another reason why we need to study redshift of 2 is just that fact that by redshift of 0, these effects of environment sort of gets saturated, and we are not really able to detangle the effect of, say, stellar mass from environment, because all of these properties like star formation are very well correlated with the mass of the galaxy as well. So we really have to look back in time to be able to see where exactly the effect of environment is starting to set in the galaxy evolution process. So for that, so now I'm going to go into the work that I did, in which I looked at a protocluster in the cosmos field, which is a field in sky, which is very highly well studied. There is a plethora of ancillary information, which is multi-wavelength on that. So we can make use of that extra data. So this protocluster was spectroscopically confirmed to be at redshift of 2, which means that there is a definite high density in number of galaxies in that certain space in both 2D as well as in 3D dimension, because of course, in images, we do not have 3D information. We need redshift information to be able to give us 3D basically how to tell if there is a higher density in 3D volume. So with the spectroscopic survey, ZFIRE, I looked at the spectral energy distribution of these galaxies. Now, spectral energy distribution of galaxies is essentially the intensity of light emitted at different wavelengths as a function of wavelengths from these galaxies. So this spectral energy distribution then is dependent upon what kind of stars are there in the galaxies, how many stars are there in the galaxies, what's the stellar mass of the galaxy, what kind of gas is there in the galaxy, and so on. So using a SED fitting code in which essentially this photometric data, which is just the imaging data in multi-wavelength observations, we can sort of understand the spectral energy distribution of the galaxies, which is sort of modeled in. And from that, we can get how much stars of what kind are there in the galaxy. And we can eventually construct how much stars were formed at what time in the galaxy's history. And that is exactly what I did. So here is an example, a few examples of the galaxies and their spectral energy distributions. I have put up 4 examples. So it's of 4 different stellar mass of the galaxy, the lowest being here and the highest being here. As you can see, within just the shape of the spectral energy distribution, we can see how different they are. And that is exactly how we study how much stars is there in the galaxy and what kind of stars are there in the galaxy. So from there, we got the star formation histories of these galaxies. So what is star formation histories of the galaxies, which is shown here? On the y-axis is the amount of star formation rate that was in the galaxy as a function of time at which it is recorded. So now I have divided because I'm trying to understand how environment affects the galaxies and the star formation in the galaxy. I have divided the sample into protocluster and field sample depending on this redshift that we have, which I showed earlier. And we can see that the lower mass galaxies here, which is shown 9 to 9.5 log solar masses, the galaxies have very similar star formation histories in the input cluster and field, which means that the low mass galaxies do not really differ in their star formation histories. Another thing to notice is that the star formation histories of these low mass galaxies is rising, which means that these galaxies are only starting to form their stars right now, which is about here. And earlier on towards Big Bang, these galaxies were not really making as much stars. As we go further along in the stellar mass bin, in the next stellar mass bin, which I've taken as 9.5 to 10, again, there is no significant difference between the star formation histories of protocluster and field galaxies. But there is, again, they have sort of a rising or a bursty star formation history, which just means that these galaxies sort of had a burst of star formation, which boosted up their stellar masses in the recent history of these galaxies. And it is actually only in the most massive bin, in which galaxies I've chosen as galaxies that are more than 10.5 log solar masses, that we see a significant effect of environment in the star formation histories. The red galaxies, which is shown here, which are the protocluster galaxies, as you can see, very early on, they made a lot more stars compared to the field galaxies, which is shown in the blue. And towards the more recent history, which is over here, we see that the cluster galaxies are not making as much stars as the field galaxies. So in the most massive galaxies, these in the cluster, they're already starting to show signs of star formation suppression, which means that they are on their journey to their eventual quenching. That is what I meant by the beginning of the end of these massive protocluster galaxies. Now, this is one of the main results from this work. In the next half of this work, I looked at IllustrisTNG cosmological simulations. So why did I do that? With observations, we cannot really pick out galaxies and look at their evolutionary histories to actually understand what is causing this sort of an effect where the massive galaxies are undergoing star formation suppression. So I looked at cosmological simulations, in which people have essentially simulated a small universe in the computer, and you can pick out galaxy by galaxy and study their evolutionary history and see what's actually happening to these galaxies. And that is exactly what I did. I looked at the star formation histories of galaxies from IllustrisTNG, and we find a qualitatively similar results that we find in observational work from star formation histories. That is that the low mass galaxies and do not really show any significant effect between cluster and field and galaxies, and they have a rising star formation histories. And it is only in the most massive galaxies that we see any significant effect of environment in the galaxies. So in that, the brown galaxies now, which show the cluster galaxies, have a declining star formation histories, whereas the field galaxies, which is shown by teal here, have a more of a rising and then sort of a stagnant star formation history. So it is only in the most massive bin that the protocluster galaxies are starting to show signs of star formation suppression, which is what we saw in the observations as well. Now, this can, which is just a comparison here. Now, this can happen due to various different reasons. One is that the cluster galaxies were simply formed earlier. So because they were formed earlier, they kind of go through their star formation and quenching earlier than the field galaxies. So to test that, we looked at the stellar ages of these galaxies in IllustrisTNG. And we find that the massive galaxies most definitely were formed earlier, about 190 million years earlier. But between cluster and field environment, the stellar ages are not very significantly different. So that means it's not that the cluster galaxies were formed earlier, and that is not the reason why we are seeing this effect where they are showing signs of star formation suppression. Now, as we mentioned earlier in the beginning, that galaxies that are in cluster region can go through different encounters with other galaxies, which can cause star formation suppression. So I looked at the merger histories of these galaxies, and we find that the cluster galaxies again do not significantly differ in their merger histories compared to the field galaxies. Although in the most massive bin, which is shown over here, we do see a slight increase in the number of mergers or number of major and minor mergers, which just defines by the mass ratio of the galaxies that are actually merging together, which has an effect of how the star formation will go on in the resultant galaxy. But it doesn't look like there's a very significant effect of mergers as well. So the signs of star formation suppression that we are seeing here is definitely not an effect of these kind of encounters. So then I looked at the types of mergers. So basically looked at the gas fraction of the mergers, which just means the gas fraction of the two galaxies that are merging together, or many galaxies that are merging together to form the resultant galaxy. And because the gas fraction of the galaxy merger can define how much gas is being supplied into the galaxy, and if that will actually boost star formation or lower star formation. And now I tested that by looking at the cold gas fraction of the galaxies in the mergers, because cold gas is what is required for making stars. And so again, y-axis shows the number of the fraction of mean cold gas, and x-axis now again shows the stellar mass of the galaxy. And again, there is no significant difference between environment in the within the stellar mass bins. So even the cold gas fractions is not actually driving the signs of star formation suppression, although we are seeing in fact that most massive galaxies have slightly lower cold gas fraction in the galaxies, which can show star formation suppression, but between cluster and field it's not very significant. And so I looked at all of the gas in the progenitors. Progenitors are basically galaxies that kind of merge together to form the resultant galaxies. And so now again, on the y-axis shows the total gas fraction in the progenitors of the galaxy, and x-axis is the age of the universe. Or basically I'm plotting how much total gas was supplied to the galaxy through the merger histories to see at what is differing between cluster and field environments. And it is within these that we find that the most massive galaxies, which is shown here in the solid blue lines and the brown lines, that the cluster galaxies have a consistently lower gas fraction in their progenitors compared to the field galaxies, which is shown in the solid teal line. And this has been happening since very early in the universe, almost since when the universe was 1 gigayear old. Which is when the universe is usually very gas rich anyway, but still for some reason galaxies that are in the cluster are not able to get as much gas from the environment that they are in compared to the field galaxies. And the signs of star formation suppression that we are seeing over here is probably an effect or a delayed effect or a cumulative effect of what we are seeing in the total gas fraction in the progenitors. So I'll just quickly summarize my results. In both observations and simulations, we see that the massive protocluster galaxies are starting to quench or starting to show the signs of star formation suppression. This is not a result of early formation and evolution of cluster galaxies as we thought, but it is probably an effect of low gas fraction in the progenitors of massive protocluster galaxies. And with that, I will stop talking and take any questions if you have.
Thank you very much, Anishya Di, for a wonderful talk. Yeah, Bagla sir has his hand raised, so he can unmute and ask.
Yeah, Anisha, there was a recent paper where they studied, and this was using simulations, they studied the quenching as you get into, as galaxies get into clusters. And they found something interesting that filaments, which are kind of clusters are at nodes of filaments.
Yeah.
And the filaments kind of creep into the cluster till quite some distance, and galaxies which are moving along those filaments don't get quenched so easily.
Yeah.
So is there any observational evidence of this?
Observational evidence for that is there for lower redshift universe, but not so much in the high redshift universe, because just to clarify, like to classify galaxies as protocluster itself is quite of hard to do. So yeah, so filaments in high redshift is not there, but in the lower redshift universe, galaxies that are in filament region are definitely still forming stars, because they have more gas flowing through them. And that is something that I looked at in TNG now. So that's what I'm working on right now. And I'm seeing that as galaxies are falling into the cluster, if they are not near the cosmic web, then they do not get as much gas. And this is an effect that's been going on since very early in the universe, like 1 gigayear.
No, what I meant was that filaments kind of inside the intracluster medium.
Oh, inside the intracluster medium.
Yeah.
Oh, okay. No, I do not think within the intracluster medium, I have not really seen this as observed even in low redshift universe. But it might just be something that I've not come across, but it does make sense. We might be able to see it further if we have like more high definition, like more high resolution, spatial resolution images of the low redshift galaxies at least.
Certainly.
And the cosmic web, yeah.
Okay.
Sorry? Yeah.
Thank you.
Does anyone from offline audience have any question? Okay. We'll move to the online audience. Does anyone from online audience have any question? I'll just be walking. Yeah, so I had a question about this one graph that you showed that was between star formation rate versus the mass of the star in the previous slides in like the first half of the talk.
This one?
No. Yes. So can you explain what is the IRC and Z-Purge and what the plot,
sure.
what it elaborates on the plot?
Yeah, most definitely. IRC 0218 is just the name of the protocluster that is being studied here. And the Z-Forge is the survey from which this is taken, or the field sample is being taken. So the star formation rates that is measured on, plotted on the y-axis, and star formation rate is on the y-axis, and x-axis shows the stellar mass of the galaxy. So basically, the red shows the cluster galaxies that are from this IRC 0218 protocluster, and the blue galaxies are the field galaxies or isolated galaxies, and that data has been taken from the Z-Forge survey at redshift of 2.
Okay.
Does that answer the question, or should I?
I think I understand it a bit. Probably I can contact you later if I want to ask you.
Yeah, most definitely.
Yeah, great. So if no one else has any questions, so we can probably move towards the next talk.
All right.
Yeah. Thank you very much for a wonderful talk, Dee.
Thank you so much for inviting me,
Yeah.
and I hope you all having a good time.
Yeah, same to you. Yes. Komal's talk is still, it will start at 10:45. Is she here? Komaldi, are you here?
Yeah, I'm here.
Yeah.
We'll start in 5 minutes.
Yeah, great.
Yeah.
So we'll probably take a break of 5 minutes and we'll start exactly at 10:45. Yeah, so I guess we'll start now. I'll invite Shantanu from MS 19 to introduce Komal Bali.
Hello, everyone. So for our next speaker, we have Komal Bali from the batch MS18. And the title of the talk is Exploring Exoplanetary Atmospheres. So a little bit about Komal Didi. She's a fourth year student at ISMOHALI who's pursuing her major in physics along with a minor in data science. During her core years, she has explored many different research topics. And by the time she reached her major years, she settled into astronomy. She has been working on transit light curves of exoplanets, exoplanetary atmospheres, planetary atmospheres, mainly of the Titan, which is the Saturn's moon, and is hopefully focusing her thesis around exoplanets. She likes doing outreach work for encouraging women in STEM, particularly astronomy, by writing articles, tweeting, conducting talks and seminars. So I hand it over to Komal.
Yeah, thank you, Shantanu, for the introduction. Hello, everyone. So today I'll be starting my talk now on the topic exploring exoplanetary atmospheres. So I'm thankful for for the invitation to the symposium, and I'm happy to present my work here. Today I'll be presenting some of the work which I've done with in collaboration with Dr. Caitlin Ahrens, Dr. Vincent Chevrier, and Dr. Mikkel Kama. So my slides are visible, right? I didn't ask.
Yes, they are visible.
Okay, great.
Yeah,
Thank
they're
you.
visible. Yeah.
Yeah. So first of all, I'd like to give a short history of my journey till now. I mean, it's very short, but still, I started with bits of work like in evolutionary biology as well as biophysics almost together. But then I moved into condensed matter. And then finally, in my third year, I ended up working on exoplanetary transits and exoplanetary atmospheres. And currently, I'm working on transits, atmospheres, as well as planetary atmospheres. And hopefully, we'll be working on exoplanet detection instrumentation very soon. And all of this I found very exciting. Like whenever I was doing all other works or topics I was exploring exploring, I was like, okay, this is fine. But when I started working on it, I felt very nice. I mean, I don't know. What is it? Is it that some work is made for you or you are made for some work? I don't know. But I felt like that. And moving ahead, I'll be first introducing what are exoplanets. Since this is a new field and there's not much work being done in India. So I'll introduce exoplanets. So exoplanets are also called extrasolar planets, planets which are outside our solar system. And why are they important? Because we want to know, is there any sign of life outside our own solar system? So that's why these are being studied. First exoplanets were detected around 1990s. There were around 2 exoplanets detected at that time. And the closest exoplanet to Earth is Proxima Centauri b, which is like around 4 light years away. Exoplanets are mostly found in a very small region in our own galaxy, Milky Way. Or I don't know what is the reason for the statement said by the scientists, but I think it is mostly because we haven't been able to detect very far. Our techniques are yet limited to a small region of the Milky Way galaxy. And talking about exoplanets, they come in a wide range of size. They range from like very small rocky planets like Earth to large gas giants like Jupiter. And based on sizes, exoplanets are mainly of 4 types. They are gas giants, as I said, which can be of the size of Jupiter or can be even larger than the size of Jupiter or Saturn. And then there are terrestrial rocky planets, which are Earth-like exoplanets in terms of sizes. And then there are super Earths, which are more massive than Earth, but they are less massive than Neptune or Uranus. And then there are Neptune-like, which are around the size of Neptune and Uranus. The temperature of exoplanets has huge extremes. It can be super hot and it can also be super cold. Some exoplanets have very tight orbits, like they revolve around the host star very, very closely, that their orbits last around 1 year, last around only a very few days. And while some exoplanets on the other extremes are rogue, like they don't have any orbits, they're just wandering in the galaxy with permanent darkness. Here I've shown exoplanetary transit light curves. So when an exoplanet comes near its host star, there is a dip in the light intensity observed of the host star, and that causes a light curve, transit light curves. So these are 2 transit light curves which are obtained for one of my work. I obtained many, but I just presented it too. I mean, this is to show the variation in the transit light curves. Like the shape is very, very different. Like every exoplanet has its own distinct shape of the transit light curves. Now, coming about detection, exoplanets are mostly detected through 5 ways, and they are radial velocity, transit photometry, direct imaging, gravitational microlensing, and astrometry. But direct imaging and other techniques detect only a very handful of exoplanets. Mostly the exoplanets are detected through radial velocity and transit photometry method. So in radial velocity method, near its host star, it causes the star to wobble in space, which changes the color of the light which the astronomers observe. So in that way, we can know an exoplanet is passing in front of an host star, and we can see the change in the color of the light and detect it. And in transit photometry, there's dimming in the light intensity, as I previously showed in the transit light curves, which helps us detect exoplanets. Also, I'll talk about direct imaging. It's just basically taking pictures and removing the glares of the stars which the planets orbit, and we can detect exoplanets that way. In gravitational microlensing, that light is bent by using gravity and focused when a planet passes between a host star and the observer. In astrometry, there's wobbling of host stars when planet passes, and then its relation to other stars in the galaxy is seen, and then we compare. And these are the various ways by which exoplanet is detected. Now coming to exoplanetary atmospheres. Exoplanets are made up of elements which are similar to those present in our own solar system. But the mixes and the variation and the composition varies. That is why we are working on exoplanetary atmospheres, because the elements are similar. Only there is the ratio and composition is different. So we can, find patterns. What are the patterns there? Simulate them, and then maybe detect them with the future telescopes and compare our data. Mostly like we can see a large amount of variation in the atmospheres as well. Some are dominated by water and ice, while some are dominated by iron and carbon. There is a huge diversity. There's an astonishing diversity in the planetary masses, radii, temperature, orbital parameters in the exoplanetary atmospheres, which helps us in exploring more and more worlds. Like you just can't predict. If you go and think, okay, this is something I'm gonna work on, you have to see a lot of parameters, because there is a lot of variation. This is like, you don't even know what is happening on Earth. You can still have data. The exoplanetary data is very less right now, and this is the transmission spectrum which I obtained for one of my current projects. So this shows the radius of the planet and the radius of the star ratio varying with the wavelength. So this is the spectrum like which we obtain, which helps us in predicting the various orbital and planetary parameters. So I'll be talking about the principle of transmission spectroscopy. By the transit methods, we can find out the radius of the exoplanet or the size by radius ratio of the exoplanet. So how is that important? So when there is a decrease in the brightness of the star, we can measure the radius of the planet. But then again, that radius of the planet is dependent upon so many factors. So in that way, we can find out the thickness of the planetary atmospheres, which in turn is dependent upon many factors like pressure temperature profiles and the chemical abundances in the planet, like what are the properties of the atmospheric gases present in the atmosphere of the exoplanet, what are the absorption properties of the particles present in the exoplanet. And thus, that is why we go for wavelength dependent planetary radius. So we make transmission spectrum and dependent upon wavelength, and thus we can find out various properties which are hidden behind the planetary atmosphere. And now, Titan-like exoplanetary atmospheres. Why our work is going on Titan-like exoplanetary atmospheres? So Titan is Saturn's largest moon and the second largest natural satellite. It has a very thick and atmosphere dominated by nitrogen. So Titan also boasts this hydrocarbon rivers, which can potentially serve as the harbor of strange life. It has subsurface ocean layers of water, which can also, maybe support life like Earth there. So there's a lot of speculations going on that whether it can be a harbor for or a signature for new life there, or like setting life already there. Also, the future telescopes tend to predict that there is a smoky haze in the Titan like exoplanets, and that can be uh, found out very soon. Like if the telescopes data come, what are the predictions going on, that we can see a lot of smoky haze in the Titan like exoplanets. So that is a very good factor for exploring Titan like exoplanets. So this is an artist's rendering of NASA's Cassini spacecraft observing a sunset through Titan's hazy atmosphere. The project which I did, because it has to be part of a very small pipeline, like it doesn't have to be detecting life there. So it was first to find out the data recorded using the PSG, which is the Planetary Spectrum Generator, and to see if the spectral irradiance or the collision induced absorption changes based on haze or any other atmospheric compounds abundance. So to find out patterns is a very important thing, because if we can observe a pattern, then we know that there is something going on there. There is some particular pattern being followed, means there is something specific there. So I was finding out patterns in the data. What is PSJ? It is a spectrum calculator by NASA. It is an online tool for synthesizing and retrieving planetary spectra, atmospheres, and surfaces for a broad range of wavelengths from any observatory like JWST, ALMA, any orbiter, ExoMars, or any lander. And the range of wavelengths is very broad, like UV, visible, infrared, and it can cover all sorts of wavelengths. And this is screenshot of the PSJ. It has vertical profile with 47 layers of atmosphere. So in the calculator, one can vary any of the atmospheric components with any abundance, with any pressure, with any temperature. And there are a lot of other things, like many things to explore there. Even I haven't been able to explore the full calculator till now. And this is just a screenshot showing the vertical profile of the atmosphere. So the data details, how I took the data, I used the ALMA template in the PSJ, and I mainly focused on CH4, C2H2, N2, and HCN. I also then varied the haze grain size. There is also option in the calculator to have hazes and vary their abundances or the sizes. I used 0.01 micron, 1 micron, and 10 micron. Temperature which I varied was 50 Kelvin, 93 Kelvin, and 200 Kelvin. So what I did was I took all these atmospheric gases. I first put their abundance to all same, say 5% abundance, and then varied one of the abundance each by making it very large, say 50%, and then use different combinations of this radii and temperature and obtained a whole large set of data. And then I made the plots of size by abundance of haze to the spectral irradiance, and I plotted them. And I also used it for HCN. And then I also used the semi-log plots for further, seeing whether the variation is prominent or not. Seeing the semi-log plots, it's easier. The observations also involve that the frequency which I used in this or this calculator used for this simulating spectra was around 363.8 gigahertz. And the trend line which was observed for gases like CH4, C2H2, N2, when their abundance was kept higher in respective to the other gases, was found out very similar. And it was like increasing. As you can see in this plot, in the semi-log plot, the spectral irradiance is increasing with the size and abundances. But when HCN was taken into account, when every other atmosphere's composition or abundance was kept around at low percentages, and only HCN was increased to till 50%, then the plot showed a different trend line for spectral irradiance, which is more clearly visible here in this plot. So as you can see, there is an increase in the spectral irradiance here in the log plot, but there is a decrease here in the HCN one. And this was found out similar for haze and also for HCN graphs. So the graphs are different for hazes and HCN. And from the data set, it was observed that the spectral irradiance of 5% methane and 5% HCN was 5.48 Jansky, whereas the spectral irradiance of 5% CH4 and 50% HCN was 5.85 Jansky, and which further implies that there is higher solar flux and HCN in the higher layers of atmosphere. There was also seen a peak in the spectral irradiance as the haze abundance was increasing. So there's a question going on. Does the spectral irradiance with increasing haze always have the same point of change around that 70% as abundance, or like when CH4 and HCN abundance change? Like, is there a pattern? Like, do we observe it all the time when things and parameters are changed in such way? And does this point of change also vary when haze particle sizes changes? So that's why I was using different sizes of haze particles, because we need to see the pattern if it is being observed everywhere. And further, I'm still working on this. So right now I'm trying to explore the terminal velocity parameters. For that also there is some online tool, which is a very nice tool. For I've not yet started using that, but like I will be using that to know the terminal velocity of the haze particles through the different atmospheric scenarios. Like, how does a haze particle fall differently with an atmosphere with more HCN versus an atmosphere with more CH4? So these will all give us further patterns to the exoplanetary atmosphere of Titan, like exoplanets. And the future of exoplanetary research, I haven't planned a summary for my talk because the work is still being done. There are no prominent like finishing results, but I do want to highlight on the fact that there's an unprecedented revolution in the field of exoplanetary research. And with James Webb Space Telescope coming up, there can be further exploration of atmospheres of exoplanets to search for the building blocks of life elsewhere in the universe, to look for the signatories in outside of our solar system, which will be very interesting and exciting. And okay, I'm ending the science part here, and I'll be coming to the non-science part. So I'm not very senior, and I'm not pursuing PhD right now to give some very prominent advice, but yeah, I'm still majoring. And some sort of advice I would like to give is that never hesitate to ask for help or advice. Do approach your seniors or your friends or teachers. They are very welcoming. Like, I know there is some hesitation initially in the core years or in the start of major years, and pandemic may have given even more restrictions, but do approach faculty and seniors. You will always have different views, and you will always feel benefited by talking to other people. And don't restrict yourself to one topic. Don't think like, okay, I'll work in this particular topic only, and I'll work in this till my 5th year and further. This is a very long journey. You'll end up getting saturated, as I've seen in many examples. So keep exploring, because you're still in your undergrad. So you have a lot of variety. There are many people working in many different fields. Explore them until you find something good enough to start your thesis. And since now minors are being offered, or courses get offered in different semesters, and sometimes they don't get offered, so be aware of when any course is being offered, because I've seen it with my batchmates and with me also, like trying to, okay, this is the course being offered now, I'll take it in the next semester and all, but then you need to plan it. When you start your major year, have a plan in front of you. Make plan A, plan B, just write it down. I found that very helpful, because I was confident in choosing courses, and even have planned ahead which courses will I take in my next 2 semesters. This is very helpful. And I've seen people suffering because they missed out on important electives which could help them in their research work. And that internship period is very, very, very important. As seriously we take our courses, we should also take the research work, because we are in ICER. Our goal is to balance our courses as well as our research work, because we'll be contributing to the research community at the end of our 5th year. And also recreation is a must. Do take part in various activities, extracurriculars. Go to conferences, attend them online if they are virtual, and take part in this club events, and do ask questions when you can. And this is a picture I have attached. So in March 2020, like several of us from Astronomy Club, we went to a conference in IIT Mandi, and we ended up like spending 3 days there and enjoying hackathons, talks, quizzes and many other events. And then this is a behind the scenes image when we were going from one campus to the another, and we were just posing for the photographs and then removing our masks because COVID was just about to, like, the lockdown was just about to begin. So this is a short memory of before lockdown. Yeah, I think if you have any questions, you can ask. I think I'm done. Yeah.
Thank you very much, Komaldi, and thank you for this picture also, which is like a great memory. So,
Yeah.
Bagla sir can unmute and ask.
Komal, thanks for the interesting talk. Given that adding a single molecule or removing a single molecule can change the curves so much, do you think it is reasonable to work with this kind of a model? Because there is an endless supply of molecules if you talk to a chemist, which could exist in an exotic atmosphere, and that could change the whole scenario. So is there some work being done in kind of exhaustively scanning molecules which could exist in atmospheres?
Yeah, I think there's some work being done, but that's not coming to my mind because I don't know exact, so it would be wrong to mention any of them. But yeah, I understand your point that even if a single molecule can do a lot of changes, why are we not, like, what is the credibility of such models? So this is like what I did was I did it on my own individual level with my own collaborators, with some simulations with the calculator. This was finding out patterns with 4 or 5 gases. But there are many gases which have been explored and which I have not even heard of. So yeah, this is some pattern which we are finding with 4 or 5 components, and then we can further expand it to even taking more gases, because we cannot take all the gases at one point of time. So we have to decide, okay, these are the parameters, these are the assumptions. Which one do I need to take into account into my model first? Which will be the initial assumptions? Because this is not just like, okay, I did this 4 or 5 gases, but it's over. No, I'll be definitely expanding it to taking into account not all, but as much as other parameters I can. So yeah, I mean, this is just like starting. So I'm taking this 4 or 5 components, exploring them, seeing their patterns, and I'll be taking into account more components, exploring their patterns. But I think, as you said, I don't think this will ever get over. So like, yeah, more and more people will do such things, and then they will find out various models or build them. And I'm currently also working on one of like grid system model, like forward modeling, backward modeling, which in which there are many chemical abundances being taken into account. There are like 200 plus chemical abundances being taken into account. But yeah, and that also initially I'll be working on some limited abundances, because I cannot work on take into account all the abundances. But yeah, like people I'm working with, they have already done that in their own thesis or PhD time. They've worked with all the 200 plus parameters. So yeah, there are some models there. I can maybe share you over email.
Yeah, thank you.
Yeah, thank you.
Harvinder ma'am also has a question, so she can unmute and ask.
Hi, Anisha. Just a minute. Yeah. So, Anisha, I wanted to, sorry, I'm sorry, I wanted to say hello to Anisha before. Komal, I wanted to ask you one thing. So, around 5,000 confirmed exoplanets are there.
Yeah.
So, there is data enough to basically classify their properties according to their atmosphere and all. So, is there any work done which actually classifies all these based on their environmental properties, so on and so forth?
Yeah, there are many papers on that. I think people have done work on that. I think Niku Madhusudan in London, I think he has worked on classifying the atmosphere, the exoplanets based on the atmosphere, and then many research papers on that. But yeah, I mean, like, and there is work being done on that also. Yeah.
So are you, sorry, are you aware of references and results from there?
I've not gone through, but I've just seen the papers, but not gone into the details. So I don't know the exact like results, like what are the exact results. So maybe I can share you some of the links if after the talk. That would be better, because I'm still exploring it. So I don't know of all the results that are out there. But yeah, I know work is being done. There's some uh, Niku Madhusudan. I think he has done some plenty of work in this. I've seen some papers.
Okay.
Yeah.
Rajnil Mukherjee has raised his hand, so you can unmute and ask, Rajnil.
Yes, I have a question. Like for exoplanet, like if it were to support life of any form, how drastic can its conditions can be as compared to Earth? Like the maximum difference in conditions. I know,
I mean,
to understand the kind of life which it needs to support, but still, like any idea.
there can be any condition. It's not just like Earth. The exoplanets can be like Jupiter. They can be like Saturn. They can be like even the moons of other planets. So there are many exoplanets. So it's not just Earth. So you can expect, if they're not even just like Earth, they're like many other planets also. So you can expect the variation. If it was just Earth, I could still say, okay, this is the mass range, this is the temperature range. But no, that's just not like Earth. There are like many other planets in the solar system as well. So there is a huge variation, like a very big variation. So like there can be cold that they can be like deep freeze. They can be locked in deep freezes, or they can be as hot as, like, metals can even boil there. Like if you keep a metal in the atmosphere, it will start boiling. The exoplanets can be that hot as well, and they can be super cold as well. So just to say, yeah.
Oh, okay. Thank you, Vivi.
Even I had one question regarding, I wanted to ask, you studied 2 exoplanets in your project. So I wanted to ask if there was any particular process to choose the exoplanets, or were they assigned to you, or how?
Okay, are you talking about the exoplanetary transit light curves?
Yeah.
Where I mentioned, so that is just, I showed here 2 planets, but I wasn't like given any specific. I could work on that was taking out light curves for exoplanets. So there is a package called K Transit. It has a directory of around like 100 plus exoplanets, or even more, I guess 200, like around in the range of 100 to 200, and it has all the information about the needed, like for the light making the light curve, or the transit depth, and all those information. So with help of those, I was just playing around with whatever exoplanet names I liked, or
Okay.
like, so yeah. So I just put in there two exoplanets, but I've even made out plots for even more. So yeah.
Okay.
Yeah.
Does anyone from offline? Yeah, you can come and ask.
Hi, Komaldi. You talked about
Hi.
you talked about this exotic hydrocarbons that may potentially harbor life on Titan, right? So my question was, what sort of instigates the formation of these hydrocarbons in the atmospheres, and is there any pattern or some specific processes that you look for, which may sort of start this process, and is there any data for the same?
I think I'm not aware of the data, but yeah, there are predictions that it is made up of hydrocarbon atmospheres. Like Titan, like exoplanets are made up of such hydrocarbon surface layers or something. So I think I'm not aware of any such data, prominent data, but yeah, the predictions. So basically we are working on the predictions, and maybe future telescopes will help us in like proving them, and then we have the data in our hand, and then we can say, okay, this is what we have, and this is true or not. We can say that.
Also, do the physical parameters of the planet sort of decide the formation of such hydrocarbons, like the size or the distance from its
Yeah, they probably decide it, like there is that dust, and it's surrounded by various other rays, and I mean there's a whole lot of this planet formation theories and all those. So maybe you can read about them and you'll get to know like how a planet, like dust particles and all, like planetary dust and all, what makes them, what accumulates outside the layer and all those things, those phenomena. They would be good to help explain these factors. So maybe you can read about that. Yeah.
Bagla still have his hand raised. So is it by mistake or do you still have question?
That was by mistake. Sorry.
Yeah. Okay. So are there any more questions from online audience? I guess not. So maybe we can move to the next session.
Yeah, yeah, sure. Thank you so much for having me here. And yeah, I mean, I'm not an expert in this field. I mean, yeah, but I've tried to showcase here whatever I know, and I hope to know more in this field. Even I'm interested and exciting. Like all these questions, I hopefully will help me also to work better in my field. Yeah, thank you so much.
Yeah. So for the next talk, we have Gowri here, and her talk starts at 11:20. So we'll quickly set up. She is an offline speaker, so we'll quickly set up the setup for her, and we'll be back in 5 minutes. Okay, so we'll move to the next talk by Gowri from MS18. I will invite Archit from MS20 to introduce her. Archit, are you here?
Yeah.
Yeah, great.
Hello, good morning, everyone. I am Archit Kulkarni from MS20 batch.
Oh, we cannot hear you, Archit. Is it problem for our end?
Hello, am I audible now?
Yeah, you're audible now.
Okay. Okay, hello. Good morning, everyone. I am Archit Kulkarni from MS20 batch, and I welcome you to the third talk in the third session of Astronomy Club Symposium. For today's speaker, we have Gowri from MS18 batch. Gowri is currently a fourth year undergraduate student at IISER Mohali. She is pursuing physics major and data science minor. She is currently working with Dr. Asaf P on gamma ray prompt emission modeling and will continue to work with him during her master's thesis. In today's talk, she will introduce us to the gamma ray bursts. She will briefly discuss how these bursts can help us in search of gravitational waves and neutrino sources. She will also discuss the experimental evidences supporting the two proposed mechanisms to explain the physics of the initial gamma ray emission phase. It is great to have her here with us today. With that, I'll hand over to Gowri.
Hello everyone. I'll turn off the video.
However, nobody will see you. It will be better if you keep it on. Remove the mask and be louder. Yes.
1 minute. Hello, everyone. I'm joining here from the offline session. I'll share my screen and then I'll start the talk. Okay. Can you see my screen?
Yes.
So hello everyone. Before the talk begins, I'll clarify that this is not going to be mathematically intense. It's mainly focused towards MS-20 and MS-21. So the point of the talk is to introduce you to the concept of gamma ray burst and give you a few introduction to all the main terms and like what to expect when you hear gamma ray burst. So my talk is titled as Physics of Gamma Ray Burst, Exploring Prompt Emissions of GRBs. What are prompt emissions? You'll get to know as the talk goes on. So okay, what are gamma ray bursts? So these are these extremely intense bursts of energy, say what our sun would have emitted over its entire lifetime, that emits over very short amount of time, say for 2 seconds to 100 seconds. So, and interesting fact is that these events are so frequent that once, maybe each event happens every day, maybe twice also. So imagine these highly energetic bursts happening every day, that too in short amount of time, isotropically distributed over the sky. So what could be the source of these events? This was so just to mention, to give us brief historical context. So these were first detected by Vela satellites back in Cold War era to detect radiation, nuclear explosion missiles. So those picked up these signals. So anyway, so these are isotropically distributed, and as you can see, the light curves I have given here, light curves are just count versus time curves. These are very random and non-repetitive. So what could be the source of these progenitors, or the source that produces the light curves? That's the question. So we don't know, we didn't have a particular framework to explain these. Now we are getting here. It's still an evolving field. Okay. Yeah. So I'll begin by, so my talk will be structured. I'll begin by the spectrum and I'll give you an overview of the phenomenon, and then I'll move to the theoretical part and then give you two emission models, how this could happen. So what do we see? What do we get from the satellites? So the data that we see, these spectrums are, how do we see the spectrum? So it's something called forward folding technique. So we don't know the emission process, right? So how do you model this? So you already make a mathematical function, which is so that you don't have any bias towards any existing emission models, and then you take the data counts given by the detector, and then you do a best fit. So what happens is that according to the initial hypothesis that you are taking, say here the generally used function is band function, and other band is just the scientist David Band who invented it, or a single power law function, or a smooth broken power law, or a Comptonized model. Nowadays we use Comptonized models, which are a better fit to the data. So according to your initial thesis, the free parameter values that you get, they change, and these free parameter values is what you take into account when you are making different correlations to explain the different theories. So you must have heard people saying like astro is just data analysis. So I just wanted to give you a intuitive approach, like how the data can intuit the theory, like how you can actually get insights into a process that you have no idea about. So that is what you should be like. That is the takeaway. So yeah, according to your initial thesis, your spectrum will change, your theory will change. So that is something you should be mindful about. That will be okay. And afterglows. So afterglows are essential part of gamma ray burst. There will be prompt emission part, which is the initial part of gamma rays. Then after the time goes, it will say after hours or maybe years, this gamma ray will lose its energy, and from the same location you will get an X-ray curve or a UV curve or a optical curve as the time goes on. So this is a year-long process. Whatever this initial progenitor is, the event is years long. So that is also something very interesting about gamma rays. Now we'll come to how do you go about explaining this. So fireball model is the core of any this is the initial theory. This is the core of any other modifications you are gonna do. This is mostly accepted. How is gamma ray produced? Our initial hypothesis, like our base hypothesis, is that electron-positron pair production happens given high enough temperature, and the gamma rays are produced. How this high energies are obtained, or like how this emission is obtained, is the question. Fireball model basically says that you will have an initial gravitational energy. It could be, say, from merger of two neutron stars, or a black hole and a neutron star collision, or mass falling onto the compact object, say black hole, and then this accretion. This will be producing enough energy, which will in turn get converted to kinetic energy of the relativistic outflow. Relativistic outflow is just the particles, plasma or baryons and electrons and positrons that move at high relativistic velocities. So these will be in the form of a jet. That is our current understanding. These will be in the form of a jets. Since these are jets, you can most of the papers I've seen are discussing them in terms of fluid mechanics. So that also an application of this. So the energy, the initial gravitational energy, is then converted to kinetic energy of these particles. And then these are then dissipated through radiation, some kind of emission mechanism, which gives the thermal spectrum that we see, thermal or non-thermal spectrum that we see. So thermal spectrum will be the emission by the originated through thermal processes, say black body radiation or something. Non-thermal spectrum will be through synchrotron or compact scattering, something like that. So yeah. So okay. So as you can see, what this jet happens. So this jet could be photon dominated or magnetically dominated. Whatever may be, the understanding is that these will flow, say as layers, and they will hit and have an internal shock or some similar mechanism of that, and your initial gamma rays are produced. This will give you enough energy to produce gamma rays. And then when these shocks, after it travels a while, it will hit the interstellar medium, and then this will heat up the interstellar medium and produce the further lower energy emissions, radiation. This is the general understanding. So internal shocks are mainly produced by photon dominated outflow. That is, the photons from the initial collisions will flow, and that layers will be producing that. But these we know right now that it doesn't clearly go with the spectrum that we see. but like it can, similar processes could be pursued. Okay. So usually when we have a spectrum that we saw here, these kind of spectrums, we usually in AGMs and all, we explain by a synchrotron model. Synchrotron is similar to your cyclotron, but with relativistic electrons at relativistic speeds. So we already said that there could be magnetic components in the jet, because black hole collision will somehow, I don't know the exact result, but yeah, there will be magnetic components, and these will give you a power law distribution given here, which is very similar to the which gives the peak energy very similar to the spectrums, the gamma ray spectrum peak energy. So, but the drawback of this, so people thought this was very valid. If you do a few modifications to this model, you could technically explain the other components of the variability of the curves that we saw also. But the main drawback was that when you have from the spectrum of the synchrotron, you have this low energy power law index, which is like a parameter. We know it should be -2/3 for the line of death of synchrotron. That is the lowest value you should be getting if it's like a synchrotron thing. But when you take the other gamma ray things, gamma ray spectrums, and you do analysis of it, your alpha values, most of them do have a higher value. So you don't know how to explain this. People didn't think that it had a thermal component, like it should be some kind of black body, some kind of temperature-based emission process. But since the recent studies have proved that synchrotron or any other non-thermal mechanism doesn't explain all these processes, we have started exploring thermal emissions. So I'll just give you a few other, why we came to that point, I'll just explain. So there was a study of like 2,900 bursts. They took the full width half maximum of these bursts and analyzed like how much of the GRB population do follow synchrotron, how many of them doesn't follow. That we have to know that. Maybe some of them just follow because they are just outliers. But we saw that from the study that 80% of the spectra are too narrow to be fitted with the slow cooling synchrotron emission model. And if you are including fast cooling emission method, it's 100% of them are too narrow to be complete. So here you can see these are the band function models of GRBs, and this is the black body radiation spectrum, and this is the synchrotron emission. So none of them are completely aligning with them. So you can either narrow down this in somehow, if you add some component to your theory to modify the synchrotron to bring it down, or you can like spread it out to spread the thermal emission, the black body spectrum. So these are the two things that you could do to your theory. But the thing is that it is physically impossible to narrow the broadband synchrotron spectra. So what you do is you try to it doesn't quite have the same energy as the band function, but you somehow can, by adding some components, you can spread it out and try to fit it. So the photospheric emission, as I mentioned before, when the photon-dominated outflow happens, photospheric emission model says that this emission basically happens from a photosphere, that is from distant away from this central engine. This kind of emission happens. This delay will cause changes to the spectrum, that it will be broadened somehow. So I'm not mentioning any of the maths here. So yeah. So thermal energy content of the flow is released at the photosphere. Photosphere will be like a surface around the central engine. So what happens is that this is the photospheric radius from the center. The results of this model shows that this is what we thought that could explain the thermal component that we see in the data. But what happens is that the efficiency of this photospheric emission, or say any thermal emission, is not that efficient in explaining our kinetic gravitational energy to kinetic energy to radiation energy process. So the conclusion we came to was that either thermal component you can you can add like a geometrical component, how the radiation is reaching the observer, or some kind of geometrical component to it, and you can do something about it. Or you can say that, as you can see here, this is more towards the lower energy region. So the current understanding is that for the lower part of the spectrum, there will be a non-thermal component that you can thermal component that you can fit, and when for the higher components later, there could be a synchrotron emission kicking in the jet. So there was a study by Akunar. She took a non-dissipative outflow. It's just a like a squared photospheric emission model, which is modeled by this equation. And she took the alpha values you can get from the database itself. She fitted it to the NDP line. So usually in case all the GRVs were doing a photospheric emission, it will be in this line. So when she did take the alpha values of the many other GRVs and did a fit, you can see most of them do fall in this line or above this. Below this, it will be synchrotron. So clearly there is photospheric emission is a theory that you could further pursue. It doesn't confirm that it is the only part. You can modify it basically. So around 26% of the observed points are consistent with this NDP spectrum. Like I said, your synchrotron emission probably will kick in after a point. Your earlier times thermal components often dominates. So this was the takeaway from that. This is still an evolving process. So this is, yeah, I just wanted to mention this. Yeah. Okay. Thank you. Yeah.
Okay. So thank you very much, Gowri, for this. I mean, it was a very detailed talk, and I mean, I could follow it throughout. So thank you very much for that great talk. Bagla sir has a question, so sir can ask.
Gowri, have you focused on the short gamma ray bursts or the long gamma ray bursts? That part was not very clear.
So the study that Akunar did, she did take both short gamma ray bursts and long gamma ray bursts. It doesn't really. I had done a smaller, like a shorter analysis of hers, and I had taken both of them, and it didn't show much difference in the results. Yeah.
So then how do the differences between short and long gamma ray bursts arise? Because the differences are essentially in the prompt emission.
Yeah. Yeah. The thing is that we have more number of long gamma ray bursts because they are more The number of long gamma ray bursts are higher because they are brighter. So you will have a sample set that is way more skewed towards the long gamma ray bursts. So we didn't exactly, there was a study by Derli Bigu. She did take like 32 short gamma ray bursts and did this analysis. She also got like there is a photospheric component. She didn't exactly take NDP. She took just the normal spectrum, I guess. Yeah, I can give you the reference after.
No, because the origin is supposed to be different. The short gamma ray bursts are presumed to be merging neutron star binaries, whereas long gamma ray bursts are supernovae of type 1c. So certainly the surrounding material is of a very different, has very different characteristics, and it should play a role. It definitely plays a role in terms of the long-term evolution, but it's not very clear as to how that impacts the short, the prompt emission. Yeah.
Yeah. Okay. So, does anyone else have question from online audience? Okay, Nikita has raised her hand. You can unmute and ask, Nikita.
I have a very, it might be a silly question, but Didi showed that it was 26% of the observed points were fitting. So what is the minimum percentage that we consider for a model or some hypothesis or a theory to be successful? Like, isn't 26% quite low?
When we what was it? So yeah, 26% is very low. That is why we are not saying that this is definite model. This is just it's just an initial result. For theory to be valid, I'm not exactly sure about the parameters of, like, say if you are doing we do a few Spearman test or like a t-test a few times. Like I have done that a few times, but you will have like a 0.75 more than that. Then you will say that your the correlation that you're getting is valid. But I'm not exactly sure how in this case, maybe a chi-square test. I'm not exactly sure how you will apply that, but yes, that is, it should be in that some way. Yeah, I'm not exactly sure how to answer that.
Nikita, do you want to ask anything more, or does that somewhat clarify the question for you?
No, thank you.
Yeah. Okay. Does anyone from offline audience have a question? You have to come here in front of the laptop so that online audience can see.
Yeah, so I had a question in slide 4. If you could go to slide 4, that is the fireball. Yeah. It seems like all of these mechanisms of creation of any gamma rays or whatever are all isotropic, and yet your image shows a particular beam, and you also said beam. So why is there a lack of isotropy in the emission, though all the sources seem isotropic? Or am I missing out something?
So when you say isotropically distributed, you mean the event, it's not like one event is isotropically distributed. You'll have multiple events happening all over the universe, like one black hole collision here, one neutron star collision here. That makes it. It's not the jet that is like that gives you an isotropically radiation.
No. So what I meant was a particular event within a particular event. The fireball model assumes that gravitational energy is converted into kinetic energy and then it is shot out. But why is it shot out in a particular direction? Why is it not radially outwards? Why doesn't it go in all directions? Each event.
So that there are some pressures. It's either from the because you have this collision happening. You will have pressure variations in that. I'm not exactly sure how that happens. I just know I have read somewhere that there are like these jet formations happen because of some your baryons are moving forward somehow, and some has some density differences or some type of pressure differences like that. I'm not exactly sure the mechanism.
So basically you're saying that the when the collision is happening, even though everything else can be isotropic, the collision itself is not isotropic because there is a preferred direction for the collision, and that gives a preferred direction for the jet.
More.
Okay.
Maybe someone who is like in with the jet modeling would be like more knowledgeable to answer that. Yeah.
So, yeah, does anyone from online audience? Yes.
So you told that, okay, so the distinction between long and short GRBs is on terms of time scale, right? 2 seconds or whatever.
Yeah.
Is there any difference in general in terms of a spectral feature, like the alpha beta that you see, that the short and the long GRB are similar or different thermal bond or something?
Yeah. There is short GRBs are more highly energetic compared to your long GRBs. For the spectral features, I haven't seen. Let me just for the. I don't think the alpha values varied that much. So the values I saw all. Yeah, more or less they were all randomly distributed.
What are similar?
Yeah, I think yeah, I'll have to see there's a Lee et al. Paper on like it's a catalog paper. I can do a analysis on that.
I had one question about you mentioned that synchrotron radiation cannot be narrowed down to fit the GRB spectrum. So why can it not be narrowed down?
I'm not sure about that. Yeah, I did look it up. I didn't understand.
Okay, okay, sure, no problem. Does anyone from online audience have any question? Yeah, great. So I think we can end this talk, and with that we can end this session of the symposium. So can you unshare the slides? Yeah. Yeah, great. So thank you very much, all the audience, for joining in today. Thank you very much to Gowri for being here in the offline mode, and yeah. So people can maybe write to you or contact you for the further details. Yeah. Thank you to the audience for being present to the third session of the symposium. And for the next and the last session of the symposium, we'll meet today at 5 p.m. And first talk, there'll be 3 talks that are as planned in the schedule. And yeah, let's meet at 5 p.m. Thank you so much. And I'll end this meeting now.